Going on record. Presenting. Oh, today the camera arrangement is perfect. Everyone is on the spot. Just checking that we have an opportunity to use the board. Okay. Very, very good. So.
Oh, now it's not perfect.
Well, if I will cover any imperfections, then we will not complete the course in time.
Yes.
Thank you for coming. It's great to see you, and many thanks for very inspired presentations. That your presentations kept me busy for the whole weekend, and I did upload it to YouTube, only 7 of them. It takes some time to process, but the plan is to merge them into one recording and have as an available protocol of our mini conference. That if you want to recall how to do one or another practical step, you can look at eventually. Who we are and what are we doing? We are in computational chemistry class. We covered more than half of the material. In the first chapter, we split Hamiltonian for any molecule into nuclear and electronic part, and dealt with nuclear part to go with optimization. In the second chapter, we focused on electronic degrees of freedom and went through Carter-Fock theory that allows to take into account multi-electron effects in the framework of one electron problem, with some feedback and self-consistency. And on the practical side, we learned how to build models of any molecule, how to optimize them, and how to find electronic structure in some few particular observables. So we are approaching the level of being certified computational chemist in general, but we have a little of room for improvement. We are taking the chapter on density functional theory, which is a workhorse for any calculations. It is not the top precision, but it is very practical. It's a balance between numerical cost and precision is very good, and it was so for like last 10 years. Nowadays, this theory comes to its saturation, and the world will select another standard, but it is not as quick. So it's still a lot of benefits of using DFT for a few years more. Last time, what did you do last time? Or if you scroll back, not to your presentations, but to the lecture.
ODA.
Huh?
ODA, particle and...
Well, it is not true LDA, it was Thomas Fermi. So we went through the concepts of functionals that are on background for this theory. And we made a little exhausting but generally useful background on Thomas Fermi theory, which was introduced a year after, or 2 years after design of Schrödinger equation, so at the very baby steps of quantum theory. But then no one used it because it uses some crazy approximations of a universe where electrons do not interact to each other, and where universe where there are no nuclei, no ions on the electrons. But the main outcome from this consideration was that one can make a connection between density of electrons and total energy of the system, which is the main goal of whatever we do. So those were baby games, and we are coming to a more serious true density functional theory with a little bit of flavor of rigorosity. Good. So formal density functional theory can be covered in like 3-4 sections. So 2 sections are fundamentals, why it should work, because it was a big resistance in the community telling that not each step in density functional theory is first principle, it is not derived point by point. There are some influence of human, so it is more, some people consider it phenomenological and therefore not trustable. Although this is not, well, we will not contribute to the discussion right now, but there are theorems that provide background why this theory is trustable. And we will cover through 2 of those theorems today and Thursday. If you are targeting practical aspects of computational chemistry, you can lean back, relax, and think of your drugs. It will not affect you as much. The possible benefit for your practical efforts is that you pick up the language, and if you include a little of computation as a section in your paper, you express it in a right way, and reviewers will recognize you as, like, you know, friend or enemy. They will consider you as a friend and give you green light. But what we will do today and Thursday is correct, is useful, but not practical, just fundamentals. Proving theorems. And then if anyone, a stranger, catches you on the street and asks, in your last paper you computed everything with DFT. How can I trust what you did? And you, no, there are theorems. They prove that everything was correct. Clear. No objections on general compass navigation. Practical side. Do you feel exhausted after your presentations, or it is not so bad? Good, good. I like seeing this. So why don't we do more of presentations if you like it so much? And anytime as a group you can decline making presentations, and I will happily introduce an example. Let's consider this as your free will activity that counted as additional credits towards your degree. Oh, and announcement. By now, you made so much effort with presenting and doing homeworks that if we stop the course right now, everyone gets A. So if you even missed something, you overcame the threshold for the best possible grade. So do not worry about your grades if you keep the same pace, same enthusiasm, and same intellectual level. So, next presentation. You have about a week to decide what you want to do. And here are just some general ideas. What can it be? Thank you. You're welcome. So on our practical sessions on Wednesday, we will cover the aspects of actual computations with density functional theory using new piece of software, not Gaussian, that you are masters of now, but WASP. And we will do similar things as we did in Gaussian, but we will go with different method, and we will go a little bit further. So we will not just finish with total energies and orbitals, we will go to absorption spectra and reaction dynamics skills. And then these practical skills would be nice if each of you select favorite topic and then get proficiency and share with others. And the tentative date is November 3rd, which is in how many weeks? 2-3 weeks? 2.5?
It's 2.
If everyone will feel next
7th is the Monday.
7th is the Monday. So third is a reasonable date, but until then we'll have only 2 meetings. This tomorrow, then next Wednesday I will not be in the city, and then another one. So to go through these materials, we'll have 2 meetings. And after we are done with the presentations, the rest of practical Wednesdays will be assigned to research projects. So you will have enough skills to swim independently. Yes?
Assign or choose?
I got your question. I'm thinking, generating answer. It will be, what is the right word? Cooperative.
Okay.
Good?
Yep.
So in between, choose and assign. I will offer several options, and you will choose between them. Sounds good? And if you have something in mind, you choose. What would you do if you stop trusting the instructor, or if you have stopped trusting the instructor a long time ago? On one hand, but on the other hand, you still need the subject, and you need a little to increment your proficiency in computational chemistry. You go to Wikipedia, you go to YouTube, you go to library, check out books and read them. Right? So you have a second opinion on what we will be doing today. Welcome. And it is 2 pages. It's not a specialized computational chemistry book. It is a very general physical chemistry book, which is assumed to be included in core course of any graduate program. So it's like Ira Levine, graduate physical chemistry. So it is not something super complicated. And to the next Tuesday, I want to offer you a super light and easy homework, which will be twofold. Second part will dealing with what we do in the lab, calculations, and first part will be making a summary of our today's meeting. So, like, suppose we stop the meeting right now. Then you read these 2 pages and summarize what you understand in a flowchart. So, strategy of the first theorem. This should be like 5 minutes. You can actually complete it while sitting. Okay. This squeaking noise from the seats was very well recorded in the recordings, probably louder than anything else. Where should I smile? There. So, lab on VASP, homework strategy, handout theorem. We are coming from the first Kohn theorem and his co-author Hohenberg. And if you are not in this room, you can look on the pre-recorded lecture on this address. So chapters done. We are here in the red box, and here is the tentative schedule. Today, Thursday, next Tuesday, Thursday missed, and then November 3rd, our presentations. And then there will be maybe some flipping, moving it to the next day. Here is the list of possible questions to your next presentations if you select to do so. And it is basically different ways to, different regimes of running VASP software for different models and different types of outputs. So you'll be able to modify the electronic configurations, anions, cations, doing singlets, triplets. This question 6 probably should be split onto 2 or 3 because light to matter interaction is so amazing. And also the molecular dynamics for reaction dynamics is something that some of you may get interested in. And after splitting, we will make it 10 subjects and decide what to do. So, we do not know what we are doing because we haven't defined the theorem, we haven't formulated, and we do not know where it leads to. So probably making some context and background would be first couple of minutes, and after we agree what it is, we will set up a strategy, and then we'll, at the remaining time, we'll go through boring parts of following step-by-step proof. But some humans get tired very quickly. So the boring and rigorous part should be left for later. First, we need to get to strategy and understand principles. So, brief review. Last time we placed our electrons in cages without ions and agreed that density is density of charge of electrons, number of electrons per volume, and then this density can define the total energy through our games with particle in the box. So just density in specific power, 5/3 integrated, gives total energy for unpractical universe. We want to do the same for true molecules. So introduce ions and introduce ion to electron interaction. So functionals are what? Mathematical concepts that connect function with a number. So it's correlation between function and number. For example, one can take electron density and count number of electrons. If it is one molecular orbital, it is normalized, we integrate it and get one. If because it corresponds to one electron. And here we are considering the not the most popular interpretation of quantum mechanics, where wave function square provides density of charge rather than probability. It's not quite perfect, but here for practical reasons we temporarily pretend that we believe in it. If we do the same for each orbital, then we get density of all negative charges, all electrons. 1 plus 1 plus 1. Number of electrons. Example of a function. So there are letters A, L at the end. So now, before in Thomas Fermi model, we played with only kinetic energy of electrons. Now we start believing backwards that there is an interaction between electrons and attractive nucleus, and there is an electron-electron interaction. So I'm a little lazy to draw this H2 molecule, but put positive, negative arrows between them. So a little of context and a little of language. So in in this density functional theory and in proving theorems that provide a background, they introduced a little of new notation. And since the theory has proved to be helpful, we will forgive authors of the theory for designing this new notation and making us suffer for learning new word. Although typically it's better to use the same notation. So their new notation is that instead of writing Coulomb term for attraction between electrons and nuclei, they call it with not capital E but little e, and they call it external potential. So there is a little logic behind it. So external, because they are analyzing the world from the point of view of electron. If I am electron, whoever, like walls, cages, ions are external to me. So under external, in this theory, they assume ions, potential created by ions. So here is the subject of our meeting. Here is the theorem. One of the theorems that provides background to trust density functional theory. And the theorem, even by its definition, by its formulation, it sounds a little crazy. So it tells that if you have provided total density of charge, not the wave function, total density of charge, which is much simpler. It doesn't depend on positions of first, second, third electron. It depends only on point in space. Very simple function. So if one has total density of charge, then this total density determines external potential. And it determines all observables, including total energy. This sounds very crazy. If we wouldn't look through Thomas Fermi theory, we wouldn't believe it from scratch. So from density, one gets total energy, and in between, one gets ionic potentials. Typically, we are thinking in a right direction, like providing ions, they create potential, and we find eigenstates of electrons in the given potential, right? This seems reasonable. Here, they tell, if we already know the solution for the density, then we can reconstruct which potentials and which ions did create this solution. Make sense? Or, yeah, it's like a criminalistics, forensics, looking on the fingerprint and telling fingerprint determines the person. First Kohn theorem, which is a little strange. A person is like all the minds and thoughts and weight and muscle strength, but from point of view of criminal justice, fingerprint determines the person. Right? So charge density determines external potential and total energy. Now, although we can more or less accept it as an idea, some people may not. So we would like to set up a little of formal logic to support this statement. Again, if you accept this statement, you do not need more for your practical aspects. Right now there will be just boring stuff for proving this statement. So we need to, well, if we are going forward with logical thinking, basically, since all of us are on natural sciences, it means that we hate math. Otherwise, we would go for our profession to the math. department or to logic department or whatever. But sometimes we need to take a little from them. So we can categorize the steps as what is input, what is output, and what are the formal, non-contradictory logical steps. So we should identify what is our input and what is our output. So probably as an output, we will have the theorem. Density provides energy. On the input, one can tell that to avoid some strange effects, one should say that our system, which could be molecule or something else, has a non-degenerate ground state. Because degenerate, then more complicated. What else is our input? Suppose that we know total energy. Also, there will be another input. So this theorem is based on the steps that we covered before, the variational theorem, which tells that if we know absolutely correct wave function for a provided system, then it will give the absolute minimum of energy. And if you tweak a little bit the wave function, the energy will always grow compared to the absolute minimum ground state. So this will be used as an input to the theory. So in order to make our meeting more interesting and pleasant, I better scratch something on the blackboard. Otherwise, it will be just closing the eyes, showing the screen and mumbling. I close eye, use close eyes, and it will be. So the main idea of this theorem is that let's temporarily assume that the theorem is wrong, follow some logical consequences of what follows from theorem being wrong, and arrive to nonsense. From contrary, or one of the students in this course in previous years was from with math background and from contrary, but there is a math term for this strategy. So from idiotic, meaning we suppose something wrong and then we come to idiotic conclusions, which means the original statement was wrong. And I can be wrong in this writing. Ad absurdum, no, ad absurdum, but something in this line. So the correct statement of theorem is that if you have density, that we have one and only one external potential in energy. Only one. And here we are going to throw in a statement that the same charge density may lead to two different external potentials and two different total energies. So one density leads to two potentials. Two external potentials. Then there will be a box of several logical steps. And here we are using as another input the variational theorem. So we do have function of a ground state. We know the Hamiltonian of the system. We take expectation value, obtain the minimal energy, and then any addition to wave function, say here, say there, will increase the energy. So any modification of absolute wave function will increase total energy. Any change increase energy. I do not know about you. I almost hate math and formal logic, and I'm very impatient. I don't know about you. So I'll give the idiotic conclusion right here, so that you know what to expect. And the idiotic conclusion is that E sub A plus E sub B is smaller than E sub A plus E sub B. So I don't know how to explain the level of contradiction or why it is wrong, but typically there are greatest, moral, or equal are one-to-one relations. If you have one number once and another number once, there should be equal sign between them. And here, through logic, when you prove that the number is smaller than itself, or bigger than itself. Therefore, we will set up that this statement was wrong. Therefore, there is only one potential which is determined by density. You are 95% done. The rest are boring steps. It remembers setting. So, wrong statement that we suppose there are two potentials. We have the formulation of variational theorem, and we have a wrong statement that we will obtain. Now we are trying to reproduce what is inside. So here are the steps of this logical proof. So we will suppose we will take the external potentials that we assumed in this wrong logic, plug them into variational theorem, and then do process two streamlines. One streamline for one potential and energy, another streamline for another potential and energy. And then we will add them together and suddenly arrive to wrong statement. So follow two streamlines, two equations, add together, and two inequalities. Add together, get wrong statement. So if we determine external potential, then we determine Hamiltonian, because the rest is standard for all electrons, kinetic energy and electron interaction. input, we also determine the Hamiltonian HA and HB. So here is the formulation of the variational theorem for branch A. Now, if variational theorem is correct, then any modification of the wave function will convert this equality into inequality. So we, instead of wave function A, we plug in wave function B. So here is the wave function from one branch and Hamiltonian from another branch. Now, there are no restrictions to add and subtract something. So you can add HP minus HP and plus HP. So we bring back the Hamiltonian for the second branch. And we write the variational theorem inequality. HA minus HB psi B plus psi B HB psi B. Any objections? Any corruption of logic up to now? No? We just add and subtract. So here is 1 subtracted, here is 1 added. And we can keep this term here, and this term, by the definition, is the total energy for branch B. Good. We are on our way to absurd. Yeah, we should cut just this statement and put it as a trailer for the course. So, what else can we do?
We can go for B and then add up to the question.
Correct, but let's simplify it so that last step will be quicker. The Hamiltonian H sub A is kinetic energy of electrons plus external potential A plus interaction between electrons, right? And then B Hamiltonian B is kinetic energy of electrons plus external potential V plus electron interaction. So if we subtract them two, HA minus HB will be equal V external A minus V external B. So the difference is the difference in two Hamiltonians is determined by difference in external potentials, one, because the rest is cancelled.
Why VE in both cases electron potential is same? VE is
Operator. I'm not telling about the expectation of contribution to the total energy. Now we are subtracting only the operators. Operators are not changing. You cannot change the way how electrons are interacting.
but that operator is Coulomb interaction, right? 1 over R, so R can be changed.
But the first operator is for all the electrons. Where
Interaction with let's
So
put it so V, whatever A will be, it is summation Z. Right? So external potential contains information about position of ions. The electron-electron interaction doesn't operate, doesn't depend on where the ions are. So the reverse was hence. Hence everywhere. Okay, so it is our branch A. Branch A. Is A is smaller than psi A. There are two different symbols. Here is the smaller than, and here is the angular bracket from Dirac. It's not just so much smaller. We have E, psi A plus E.
what's beside B?
Should those be side B's?
Let me concentrate. Yes, thank you. Good. One step more before we go to absurd. Let's simplify it a little bit to the language of density functional theory, to the context. So we already went to some level of craziness of trusting too much to the single word, which is density of elements. So if we do have example, I will scratch it, force it out from the proof. But if we do have electron interaction long term, so we have psi 1 at point 1 star psi 1 and psi 2 star psi 2, which will give the long, that was our favorite letter J, right? This, and there are so many integrals. This can be interpreted as potential is a potential already integrated by R1, so potential R2, multiplied by psi 2 star psi 2 R2 R2 integral. So everything that is not related to R2 can be integrated and put it as a potential. And then it is the same shape as we wrote here. So this So what we see here, we can go to this notation. And instead of wave function square, we can put just rho at R2. Right? So there are no any exchanges, there are no other contributors to this equation. So whenever we have an expectation value of potential, we can replace it. Expectation value of potential can be replaced by V times rho corresponding to branch D R integral dr. Good? So this was a little story how to simplify, which we can remove from our board, and here we continue our branch A. Branch A. E sub A is lesser than integral of difference of external potentials times density of branch B plus energy B. Any not complaints, objections, any flaws in the logic? No. Okay. Now let's do the same expression for branch B, which means we went same way, but always replacing subscript A to subscript B, and otherwise subscript B to subscript A. Branch E sub A no, E sub B. Is smaller than integral. Now we swap the order. B sub B minus B sub A. Rho, we should sort the index. Sub A. Plus E sub what? A. We are very close to final stage of idiotism. Absolute. So two small logical steps. And the last one will be adding together this expression. But before we can add them together, we need to look back on our starting point. We assume that there is only one density. So even though we consider that there are different branches of potentials, there are two branches, two values of absolute total energy, we have only one density all the time. So rho sub A equals rho sub B equals rho without indices. So because of this red box, we are removing indices because there is only one density. Good. Now this term, this integral, becomes the same in one branch and in the another, with just a little sign. So V sub A is plus here, V sub A is minus here, V sub B is minus here, V sub B is plus here. So if we add them together, we hope to get maximal level of absolute. So on the left, we have E sub A plus E sub B. Then we keep the same sign of inequality. This is logical. If it is the same direction of inequality, after adding together, it should stay here. Now we have nothing from these terms, so it will be 0. They subtract from each other. And here we have E sub B plus E sub A. So in our consideration, everything was logical. Everything was step by step correct. And should be no error. But we have something strange. Which means that either variational theorem is wrong, or our assumption of two branches is wrong. Since we have so much fear to object variational theorem, and it was serving us very well for the last couple of months, we should accept that statement of two independent branches was wrong. and although it sounds a little strange, the theorem is correct. So if one knows the density, if one knows the fingerprint, then one can reproduce which external potential has generated this density, this fingerprint. And therefore one can find any observable of the system, including excited states, including everything. One can know everything about the system just knowing the density. We are done with the theorem.
I have a question.
Please.
On top of board in black, you say that V of A of R is the sum over I, the distance between the nuclear and electronic position, right?
Mm-hmm.
But when you find the expectation value of J, you say that you're finding the distance between two electrons.
So this is not a part of our proof. The reason for this green box, the question is legitimate, and I'm very happy that I do not fear it. Sometimes there are fearful questions that one needs to answer too general and then cut this piece of recording. No, here everything is clear. No problem. So the reason for the green box was a conversion from Dirac notation with bra and cat to the product notation when one integrates potential over the density.
So
This one was only as starting example.
okay.
The conclusion is that instead of Dirac notation, one can take the potential and multiply it by density and integrate.
So you could have just done capital R minus lowercase r.
In this purple or whatever blue circle, could be and should be something different, like this
Okay.
potential. Make sense?
Yeah.
This is the hardest part to have active thinking. Yes?
So basically, they showed if you only have one density, you can only get one total energy.
Yes.
Okay. All right.
So we are halfway through for the chapter of density function. For the meeting, we are almost done. Do not expect me to mumble for another hour. No. Be a little quicker. But when we meet next time, there will be a second branch. Like, not suppose, we have proved the theorem. We know objectively that if the density is known, one can find total energy. But the question is, what is the connection? The statement that it does exist, it doesn't mean that we know the pathway how to get it. So we will need to work on this subject in more details. Where we are now. So I'm going to go to the pre-recorded slides and quickly summarize what we did. Number 3, facing podium. Jump between keyboard and the screen. So 2 branches. For branch A, we verbalize the variational theorem by using, for branch A, one Hamiltonian, one energy, but different wave function. Then we get inequality. Then we add and subtract the Hamiltonian from branch B and get 2 terms, one with difference of Hamiltonians and another with exact definition of total energy for branch B. Then we recognize the difference in Hamiltonians appears only from difference in external potentials. Because this T and VEE are operators, same forever. Now we formulate the variational theorem for branch A in term of density. So we replace Dirac notation for wave function into density. So total density for branch B multiplied by difference of potential. And then we are going to accept the fact that that in our original formulation we agreed that everything starts with only one density, one and only one density. Therefore, whatever we have A or B, density will be the same. And here we replace branches, branch A to branch B. So we replace indices. We are going to change the density A and B to simply density rho here. And then we subtract branch A inequality, not subtract, add together branch A and branch B inequality. Everything related to potentials cancels because there is only one row and the rest are just opposite signs. And we come to the inequality where a number is less than itself, which is absurd. So the statement of alternative realities is not logical. There is, if you know the density, there is only one reality, one potential and one total energy. So, and we agreed from a long time ago that in previous courses that if one knows Hamiltonian, one knows everything. And Hamiltonian is determined by external potential. Therefore, if we got external potential from the density, this means that density determines everything, meaning all properties of the system. So here is the branch flowchart that we can fill with some logical steps. And here is verbalization of the theorem. So density determines everything. Observables, density, energy, period. And if someone doesn't believe well, there are most of the scientists who are in the area believe in density function of theory, but there is a little fraction of people who continue incremental development after Hartree-Fock theory, and you may hear it on conferences or in private talks that everything that starts from Hartree-Fock is true ab initio, first principles theory. And density functional is a little phenomenological and one cannot call it true theory. Although it's a small fraction. And if someone objects some of your future results with the theory, you can intuitively convince them by the example with fingerprint, hopefully. So when we meet next time, when we meet on Thursday, we will consider additional theorem about connection between density and total energy. More details. And when we meet on Wednesday, we will master our skills in using VASP software. With this, I would like to announce completion of the lecture number 18. I will stay here for any questions and discussions, but you are free to